I want to talk about a principle known as reductive amination. It's a very cool principle and really nice reaction that we can do in organic chemistry. And we need the imine for this to occur. And if we look at an imine like this over here, which we've learned how to make from in this case, it would have been a primary amine and an aldehyde. We first of all need to just kind of recognize that an imine is really a nitrogen equivalent of a carbonyl, or in this case, of an aldehyde. So if I drew out the aldehyde which this thing came from, it would have looked like that. And we can think about the types of reactions that occur on aldehydes, but one of the interesting ones that we would do on an aldehyde is that we would reduce it, say for instance with sodium borohydride. And if we reduced it with sodium borohydride, we would end up with the alcohol. And this, of course, is a useful reaction in organic chemistry, is the reduction of carbonyls. And there's a whole bit of literature and information that we need to know about sort of our reducing agents, what we can use to do that. The question, of course, then comes in, well, if we can reduce a carbonyl, so a double bond oxygen, into single bond oxygen, can we not use the same thing in order to reduce the nitrogen equivalent into a single bond? And the answer to that is actually a resounding yes, we can. Sodium borohydride will reduce, and we would typically do this reaction in methanol as an example, will reduce an imine to the amine. So we would get this. And now it's the amine, so we protonate it over there, and we get that product. Now that's a very useful product, because if you think about it, we have effectively now brought together two different components. This R group over here might actually be quite large. It could be something small, like a methyl or ethyl, but it could be a very complicated molecule. And this part over here might have also been quite a complicated part of a molecule. And if we brought that aldehyde and the amine together, and we did this imine formation, we could then reduce it, and we would have made a molecule that then can't go back. Once it's reduced, you cannot separate or break this bond again very easily. At the imine stage, we can. Remember, imines are not particularly stable. If we have some acid and water present, they can break apart and give us the aldehyde and the amine again. So these don't necessarily stay like that. So once we do this reduction step, we can get a nice product like that. Okay, there is a problem though, of course, and that is how we do this reaction, because we know that sodium borohydride is going to reduce an aldehyde over there. So if we take an aldehyde plus a primary amine, this part over here, and we add it together with sodium borohydride, we're never going to get the reaction to occur like this. The problem, of course, is that we're just going to reduce the aldehyde, which is far more reactive. Why is it far more reactive? Why is an aldehyde more reactive than an imine? Well, an oxygen is more electronegative than a nitrogen, so the electron density is pulled more towards the oxygen, making the carbon more delta plus. This is a electrostatic type of argument, whereas nitrogen is not as electronegative, and so the pulling of electrons towards it does not make this as delta positive. So aldehydes and ketones are far more reactive than imines. We can also argue this based on an FMO argument, and it's good just to go and think about this, but oxygen is more electronegative than nitrogen. So nitrogen and carbon on the left, nitrogen on the right, the distance between them is not too big, and oxygen is much greater. So the difference between oxygen and carbon is greater, and so when they combine, the LUMO is lower, whereas when nitrogen is slightly higher, that means nitrogen has a slightly higher LUMO. The pi bond, the antibond, is slightly higher for an imine compared to the carbonyl. And so we can use both arguments to show that aldehydes are more reactive than imines. So this way of doing a reaction is actually fine, and I've done this plenty of times myself. The only thing is it does need to be a two-step reaction. So we're going to have to take this aldehyde, and in step 1, we're going to have to add our primary amine, and we're going with some acid catalyst to get it going. And then this would work quite nicely. We're obviously going to have to dehydrate. We can't just add those two together because it's an equilibrium. So we need to dehydrate somehow. And so we've got the two options of molecular sieves, or we could do the Dean stock. So those are the two things. I usually did this. Once we've made the imine and we're satisfied that the imine has had enough time to form, and we can do it, we can then throw in some sodium borohydride and we can do this reductive amination. And that's kind of like totally fine to do it that way, but there is a better way of doing it. And the issue here is that sodium borohydride is it's too reactive. It wants to react with the aldehyde. And the trick that we use is to use a slight variation on this reagent of your sodium borohydride. We use sodium cyanoborohydride, which looks like this. It's got 3 hydrogens, but instead of one of those hydrogens has been replaced with a nitrile anion. So instead of having 4 hydrogens, we've got this cyanide, and this is sodium cyanoborohydride. So why is this useful? It's useful because it's a weaker reducing agent. Okay, now that should actually be contradictory. I've just told you that carbonyls are easier to react with and imines are not as reactive. So if we're using a weaker reducing agent, that surely is not going to react with that. It's going to rather want to react with that. The trick here is that we're not actually going to be reducing the imine. The trick is that this thing works by reducing imines. So let's look at this. Now, sodium cyanoborohydride, if you react an aldehyde, so there's our standard aldehyde, and you add sodium cyanoborohydride at slightly acidic pHs, so around about a pH of around 6. So we've got a bit of acid present in this. We get no reaction. But at a pH of 6, slightly acidic, imine formation is very, very favored. But notice, because we're at a low pH, not so low, just slightly acidic, the intermediate that forms is not the imine itself. We would have to neutralize it to fully get the imine, but we actually get this, the iminium. And this over here is the key. Because remember, just in the same way as that you could take an aldehyde and you would activate it through acid catalysis. If you added a proton onto it, it made it more reactive. The nitrogen, which is basic, its lone pair wants to pick up a proton far more than this one over here. When it picks up, it also activates it because the nitrogen is now the iminium, it's positively charged. The carbon over here is way more electrophilic. And that means that when we take that and we add sodium cyanoborohydride, so also weakly acidic, around about a pH of 6, we get a very nice clean reduction to the product over there. So this is an excellent reaction, because what this means now is that in order to achieve this step, so going from the aldehyde over there to this new joined amine, we can mix all the reagents together at the same time. So aldehyde, amine, and sodium cyanoborohydride at around about a pH of 6, and we get a product forming. Let's just quickly look at that. So this example is actually a reaction that I did many years ago now, where I did a reductive amination on this molecule. There's very reasons that I wanted this, but what we have here, we've got an aldehyde, we've got an amine, and in the same reaction, and we can do this reaction in methanol as well as the solvent, just holding the pH just weakly at 6. So we just need to add a small amount of acid. It could be tosic acid that we add. We can get the imine formation and the reduction to occur at the same time. And the product becomes this over here, because we formed this new bond. This is where the reductive amination came. And so this is the beauty of this reaction, because we can bring these two parts of the molecule together in a way that works like that. Reductive amination is not the only way to kind of create this sort of bond. There is another way. It's not. This is better. It's easier because these are very reactive partners, and this is a mild reducing agent. So it's a great way of doing it. But just to show you that there are other ways that we can do this type of reaction, there's a two-step process where you could, for instance, take an acid chloride, and if you reacted that with an amine, so again, we'll just use a primary amine, this is R prime. If you did that reaction, you would get an amide being formed. So that's this. Okay, now that amide is obviously not the product that we're wanting. That's not an amine per se, but if an amide can be reduced with lithium aluminium hydride, and when that reduction occurs, we get the amine product. So we reduce out the oxygen and we get that. And so this is the equivalent of doing a reductive amination, just approaching it from a different way. So on paper, this is a perfectly acceptable way to achieve the same things. But it can be a lot nicer using this more milder process, because the reduction of amides with lithium aluminium hydride requires sometimes refluxing solvents, and the amines tend to coordinate to the salts that get formed at the end there. So it's not terribly great. So just to recap, reductive amination is a way that we can join two molecules using an amine, and it will need to be it could be a secondary amine, of course, because you can form an iminium and then you can do that. But it's typically a primary amine, an aldehyde or a ketone, and you reduce out. Sodium cyanoborohydride is the most efficient way of doing that reaction. But it is totally possible to do it in a two-step process, but it must be two steps then, where you connect an aldehyde and an amine, form the imine first, and once you're sure that is formed, you add the sodium borohydride in, and the reductive amination can take place. As with all things, I think it's a good idea for you to just go and think of your own examples. Go and make sure that you can do the mechanism of each of those steps. You don't need to know the mechanism of the reduction, although it is quite simple. It's just an H- from the boron, which is going to add N, and then you're basically there. But hopefully this helps you understand this area a little bit more.